Hello class. Today we talked about deriving additional limit laws. So yesterday I went over the first 5 laws for limits, which is very intuitive. Today we're going to derive some additional limit laws based on the laws from yesterday, and is also based on some of the laws we talked about today. All right. So first, we'll discuss repeated product law. This is kind of an extension of the product law from yesterday. So the extension is basically what happens if both functions are exactly the same. We'll get the following. We get the limit as x goes to a of f of x times f of x is equal to the limit of x, or limit as x goes to a of f of x times the limit as x goes to a of f of x. It's really no different than yesterday. Yesterday, the product law basically said if I have two functions and I multiply them together, the limits or the limit of the product of the functions is equivalent to the limit of one function times the limit of another function. Now to write this a little simpler, because if both functions are the same, we can write it like this, where the limit as x goes to a of a function squared is really the same as the square of the limit as x goes to a of f of x. Okay? The lot of f of x and x goes to a, so bear with me and hopefully it doesn't confuse you too much. Now, since this is true for a function being multiplied by itself once, we can safely extend that to a function being multiplied by itself 3 times and 4 times and 5 times and so on. And we can write more generally the repeated product law as this. So the limit as x goes to a of f of x to the power of n is really the same as the limit as x goes to a of f of x, all taken to the power of n. And it's just this is a consequence of the product law, where we just apply it several times. We just happen to have the same function every time. Okay. Now, in addition to that, we have a couple of special limits. These special limits I probably should have discussed yesterday, but decided not to. First is the limit of a constant function. So a constant function is basically just a constant, c, limit of c. C being a constant number, never changes, so it doesn't really matter what x goes towards, the limit will always be equal to c. Okay. Another special limit exists with the limit of x. So this is a function y equals x, or f of x equals x. The limit of this function as x goes to a is, well, it's just a. Because as x goes to a, it's going to get closer and closer to a. Okay. So these are some special limits. And we'll keep this in mind for the next definitions, next couple of rules. All right. So sort of combining the repeated power rule with our function of, or the special limit from number 8 of limit of x, we get the following. We get the limit of x to the power of n is really the same as the limit of a to the power of n. And a is really just going to be a number, so this will just be a to the power of n. Okay. That's our limits of a power function. Again, it's sort of a combination of the special, or rule 8 and rule 6. And we just combine them together to get rule 9. Okay. Now, if we extend this to roots, roots will just give us sort of very similar result. But with roots, you have to consider a couple of things. This is to make roots work better. For example, the index of the root, the index of the radical, has to be a positive integer. And if that positive integer happens to be even, we assume a is greater than 0. If you don't consider these cases, then this law doesn't work very well. Especially if this bit, where if n is even, a has to be greater than 0. If a is not greater than 0, then it just doesn't work. Okay. We can extend this rule to a more general case, where we take the limit as x goes to a of the nth root of f of x, and this is really the same as the nth root of the limit as x goes to a of f of x. Okay. So this is the more general case of this rule. Okay. And this really is just a consequence of rule what rule? Rule 6, the repeated product rule, because an nth index radical is really just the fractional exponent, and if we can do this with the exponent as mentioned way back in the beginning, there, if we can take the exponent outside the limit, then we can do the same thing with this one. So this one's kind of a special case of rule 6. Alright, so there we've got 10 rules for helping us calculate limits. Now, here are a couple of helpful tips for calculating limits. Now, when asked to find the limit as x goes to a of f of x, it's usually helpful to do the following in this exact order. Okay. The first is to evaluate f of a. So take whatever function you're trying to find the limit of and just plug a in. If it returns a number, that's going to be the limit. If it doesn't, well, a couple of things usually happen if this is the case. So if f of a is undefined, i.e. It's a division by 0, then sort of two possible cases exist. One is that there's an infinite limit, or an negative infinite limit, okay? Or alternatively, if f of a is equal to 0 over 0, so not just so, and what differentiates case 2 from case 3 is that this you would get some number. I really should change there we go. Okay, so this would be something, so you get some constant number c divided by 0. This is case 2. If this is the case where you have some number divided by 0, this will give you possibly an infinite limit in either positive infinity or negative infinity. Or possibly neither, if it ends up being that on one side of a it's positive infinity and one side of a it's negative infinity. Now for 3, if f of a is 0 over 0, so that's literally 0 over 0, where the numerator is 0 and the denominator is 0, try factoring. This is usually, this case is usually a clue saying you can factor. Okay? And we'll find this out in a moment with a couple of examples. Alright, for case 2, you basically just have to pick a number close to a and calculate and figure out whether it's going to be really, really large positive number or really, really large negative number. Okay, let's go through some examples where we can use some of these hints. Okay. Alright, so example 1. Example 1. Alright, so let us find the limit as x goes to -3 of x squared minus x plus 12, all divided by x plus 3. Alright, so our first step, according to my helpful hints, is the following. Evaluate f at a. So let's evaluate at a. So this will be -3 squared minus 3 plus 12 all over -3 plus 3. Oh, and this should be a positive 3. There we go. Right, so this gives me the following. This is 9 plus 3 plus 12. This will be 24 divided by 0. Okay, so this is some number divided by 0, so this is probably going to give me some kind of infinite limit. Okay? Either a positive infinity or a negative infinity. And to find out which one, let's pick a number. So let's evaluate 3, x equals negative 3.001, and x equals 3.00, or sorry, yeah, negative 2.999. Okay, let's evaluate. So f at negative 3.001 is equal to, let's pull up my calculator. There we go. So we get negative 3.001 squared. Oh, jeez. Okay. I'll use this calculator apparently. Alright. Negative. Jeez. Okay, this calculator is not what I'm looking for. Alright. Be back in just a moment. Okay. Negative 3.001 squared minus negative 3.001 plus 12 equals, oops, close bracket, divided by bracket, negative 3.001 plus 3, close bracket. So this is a ridiculously large negative number. Negative 24,007.001. So it looks like it's going towards negative infinity on the left side. On the right side, so recalculate everything. 2.999 squared minus negative 2.999 plus 12 divided by 2.999 plus 3. And on this side, on the right side, it gives me a positive 23,993. So it looks like on the left side, it's going towards negative infinity. On the right side, it's going towards positive infinity. And let's graph it to, I guess, check, make sure that we are actually doing things correctly. Alright, so x squared plus 12, x squared plus, minus x plus 12 divided by x plus 3. Okay, it looks like it is going, whoa, okay. There we go. So it looks like, yeah, positive infinity on the right side, negative infinity on the left side. There you go. Right, so this has actually no limits. Limit does not exist for this. Okay, because the left side and right side limits are different. Alright, so another example. Example 2. There you go. Example 2. So let's do this one. Okay. The limit as h goes to 0 of h minus 5 squared minus 25 all divided by h. Alright, let's put 0 in there, and right away we can see the following. Negative 5 squared minus 25 over 0. It's going to give me 0 over 0. Now this means I'm switching back here. If this is case 3, if f of a is equal to 0 over 0, try factoring and then go back to 1. So let's even factor. In its current state, we can't really factor, so I'm going to expand. I'm going to expand this binomial. I'm going to expand this. So this will be h squared minus 10h plus 25 minus 25 all divided by h. Plus 25 minus 25 disappears. So we get the following. We got h squared minus 10h all divided by h. This h, will get rid of that h and reduce that by 1. So now we get the following equation. The limit as h goes to 0 of h minus 10. And if now I can go back to step 1, put 0 in there. This is just going to be 0 minus 10, so it'll be negative 10. There's my limit. Okay, then we'll check. Let's check with a graph. So, 8, well, I guess x minus 5 squared minus 25 divided by x. As x approaches 0, it approaches a value of negative 10. Yep, there it is, negative 10. At 0, it's actually undefined, which is as we would expect, but as it approaches 0, it gets closer and closer to negative 10. So we're good. We're good. All right. One last example. Let me pick a nice this one. Last example. Example 3. Okay, so here we go. This will be the limit as x goes to 2 of 1 over x minus 1 over 2 all over x minus 2. Okay, so let's put x equals 2 into the equation first. That's kind of my first step. This gives me 0 over 0. Which tells me I can probably manipulate it algebraically and factor something out, which I will do. So let's start with just simplifying the numerator. I'm going to multiply this by 2 over 2. I'm going to multiply this by x over x. The reason I'm doing that is so I can get everything over a common denominator. So this will be 2 minus x all over top of 2x in the numerator. And I have a denominator of x minus 2. Okay. I can force this denominator down here, so I get the following: 2 minus x divided by 2x, x minus 2. Okay. From here, I'm going to multiply top and bottom by negative 1, so make that negative, make this negative. Why do I want to do that? It's so that I can rewrite the top so it looks like this, x minus 2. And this will be negative 2x, x minus 2. The great thing about that is those will cancel out. So my limit becomes limit as x goes to 2 of 1 over negative 2x. I put 2 in. This is going to be negative 1 over 4. There we go. That's my limit. My limit is negative 1 over 4. Alright, then let us check a graph to make sure things are doing correct. So the function was bracket 1 over x minus 1 over 2 divided by x minus 2. There we go. Alright, so as x approaches 2, there it is, we're approaching the value of 1, yeah, there we go. So we're approaching negative 1/4. You can see. Which is exactly what we got. There you go. So that is some additional limit rules and some helpful hints on how to find limits. Okay, today's assignment is as follows. It doesn't seem like a lot of questions, but they do require a lot of work and a lot of thought. Okay. Again, if you have any questions, come see me in class tomorrow or sometime when you have time. All right, good night.